So, what if I told you that this whole complicated world of probability, from weather forecasts all the way to quantum mechanics, is actually built on just a few incredibly simple, intuitive ideas? Ideas so clear you could literally jot them down on a napkin. In this explainer, we're going to do just that. We're going to deconstruct the rules of chance and build them right back up from scratch. And to do that, we're not going to grab some modern textbook. Nope, we're going straight to the source. We're going to crack open this 120-year-old masterpiece by the legend himself, Andrei Markov, to see exactly how he laid it all out. I mean, think about it. We all have this gut feeling for what probability means, right? We say things like, it'll probably rain, or what are the odds? But have you ever stopped to wonder where the actual hard and fast rules come from? How do we get from just a vague feeling to a precise number?
Okay, before we can do any math at all, we have to get on the same page. We need to agree on what we're even talking about. So Markov starts by building a shared vocabulary, the very foundation of probability.
First things first, the idea of a trial. It sounds technical, I know, but all Markov means is the setup, the collection of conditions. Flipping a coin, that's a trial. Rolling a die, that's a trial. Drawing a card, that's a trial. It's the moment of truth. Next, we've got mutually incompatible outcomes. It's kind of a fancy way of saying two things can't happen at the same time. A coin can land on heads or tails, but it can never land on both. This idea of exclusion is so crucial because it lets us neatly separate and count every single possibility. And here we have it, the bedrock of classical probability, the idea of equally possible outcomes. Now, this is an assumption. It means we're saying we have absolutely no reason to believe one outcome is more likely than any other. With a fair die, we just assume a 1 is as likely as a 6. Without this simple, logical starting point, none of the math works. So, once you have those definitions locked in, the formula becomes incredibly intuitive. The probability of an event is simply a fraction. You take the number of ways your desired outcome can happen, and you divide it by the total number of things that could possibly happen. Favorable cases over total cases. Simple, elegant, and really, really powerful. So, we've got our vocabulary, now we need the grammar. How do we combine these simple probabilities to answer more complex questions? Well, it turns out there are really only two fundamental rules you need to know. The first one is the addition theorem. This is your OR rule. The probability of one thing or another mutually incompatible thing happening is simply the sum of their individual probabilities. So, what's the chance of rolling a 1 or a 6 on a die? It's a chance of a 1 plus the chance of a 6. That's it. Markov makes this super concrete with his classic urn example. To find the probability of drawing any white ball, you just add up the individual probabilities of drawing each specific white ball. It's just the addition rule in action, plain and simple. The second rule is the multiplication theorem, and this one is for your AND questions. What's the probability of event A and event B both happening? You multiply, but, and this is a really key detail, you multiply the probability of the first event by the probability of the second, assuming the first one already happened. This is the whole concept of conditional probability, and it is absolutely essential.
All right, so we get how a single event works, but things get way more interesting when we start repeating them. What happens when we run a trial over and over and over again?
We know how to calculate the odds for one draw from an urn, but what happens if we draw twice? Does the logic stay the same? Well, it depends. And here is the critical difference. On the left, we've got independent trials. When you draw a ball and you put it back, the odds for the next draw stay exactly the same. But on the right, with dependent trials, you don't put it back. That first draw actually changes the makeup of the urn, which changes the odds for the second draw. All of a sudden, the past influences the future. This is it. This is the climax of our journey through probability. All of these definitions and rules, they all build to this one single idea. One of the most powerful ideas in all of science, the law of large numbers. This is what connects our abstract math to the real messy world. To understand it, we first need this idea, the most probable number. In a whole bunch of trials, it's simply the outcome that has the highest mathematical chance of occurring. So if you flip a coin 10 times, the most probable number of heads is 5. But as we all know, you won't always get exactly 5, will you? And here is the law itself. Now, the language is a bit academic, I'll give you that, but the idea is breathtakingly simple. It says that the more times you repeat a trial, the more coins you flip, the closer your real-world results are going to get to the theoretical probability you calculated on paper.
And what's more, the theorem says the probability of this happening, the probability of your real-world results actually matching the math, gets closer and closer and closer to 1. It becomes a near certainty. This is how casinos build their business, it's how insurance companies set their premiums, and it's how pollsters can predict elections with surprising accuracy. With enough trials, chance becomes certainty.
But a law this powerful often gets misunderstood. So Markov ends his work with a crucial philosophical warning about what probability is not.
Markov is very direct here. He warns against inferring a necessity of compensation. In other words, chance has no memory. If you've had a string of bad luck, the universe doesn't owe you a win to balance things out.
He gives this perfect example. Imagine a fair coin. It hasn't landed on heads even once in 20 flips. You'd think it's due for a heads, right? Absolutely not. The coin doesn't remember the past 20 flips. For that 21st trial, the probability is still exactly 1/2. Each independent event starts completely fresh. So this leaves us with a fascinating paradox. If probability can't predict the next coin flip, or the next roll of the dice, or the next card drawn, what makes it one of science's most powerful and predictive tools? Well, the answer lies in that jump from one trial to many, from pure chance to near certainty.